Okay, in today's lecture, we'll cover the last section of our Chapter 4 materials, Section 4.8, which is on Lagrange multipliers. So as we saw in our last section, in a lot of applied problems, we are interested in finding the maximum or minimum value of some function of, say, 3 variables, where we might have some constraint on our variables of the form g of x, y, and z is equal to a constant. So examples that we saw in our last section were maximizing the product of 3 numbers whose sum was a given constant value, or maximizing the volume of a box that had a surface area that was equal to some constant value. So a lot of applied problems will involve optimizing some function subject to a constraint. Now we saw in the last section, we could, in some cases, solve our constraint equation for the variable z in terms of x and y, and then substitute into our function f to get a function of 2 variables and find our extreme values as we did in section 4.7. But it is not always easy to solve this constraint equation g for the variable z or any one particular variable. So another method we can use to optimize a function subject to a constraint would be a method known as the method of Lagrange multipliers. And before we can introduce that method, let's introduce a theorem which our method is based on. So this theorem is known as Lagrange's theorem in the case that we have one constraint. So it says if we have 2 functions f and g, which are both continuous, or they have continuous first-order partials, and f, the function that we're trying to optimize, has an extremum, that is a maximum or a minimum, at some point x naught, y naught, z naught, which lies on the curve or the surface defined by setting our constraint function equal to some constant. As long as the gradient of that constraint function g is not equal to the 0 vector, then we are guaranteed there is some number lambda such that the gradient of f at the point where we have an extremum is equal to lambda times the gradient of g at that point where we have an extremum. And this constant, lambda, is called a Lagrange multiplier. So what this theorem says is if we have an extreme value of our function f at a point x naught, y naught, z naught, and that point lies on our constraint curve or constraint surface, then the gradient vectors of the function that we're trying to optimize and our constraint function have to be scalar multiples of each other at that point where we have an extremum. So this theorem gives us a method for trying to optimize functions subject to some constraint. And this method is known as the method of Lagrange multipliers in the case that we have one constraint. So here's what it says. If we're trying to find the extreme values of a function of 3 variables subject to some constraint of the form g of x, y, z is equal to a constant, we will first find all of the values of x, y, z, and lambda such that the gradient of f is equal to lambda times the gradient of g. So we know by Lagrange's theorem that if our function f has a extremum at any point, then that equation has to be satisfied. The gradients of f and g must be scalar multiples of each other. And we also have to satisfy the constraint. G of x, y, z must be equal to k, whatever constant constraint we're given. So we can solve the system of equations to find all the points x, y, and z which would satisfy those equations. And then we would evaluate our function at each point x, y, z that we just found. and the largest of those values would be the maximum value of our function, and the smallest would be the minimum value of our function satisfying that constraint. Now, when we apply this method, the first equation that we're looking at is the equation where the gradient of f is equal to lambda times the gradient of g. So let's think about what that equation really says. Typically, it gives us 2 or 3 equations which must hold. And the reason is, if we look at the gradient of f, well, the gradient of f is the vector function whose components are the partial derivatives of f with respect to x, y, and z. And setting that equal to lambda times the gradient of g, well, we would have lambda times the partial derivative of g with respect to x, lambda times the derivative of g with respect to y, and lambda times the derivative of g with respect to z. So in order for these two vectors to be the same, their components must be the same. That is, the partial of f with respect to x is lambda times the partial of g with respect to x. Now for the second components to be equal, the partial of f with respect to y has to equal lambda times the partial derivative of g with respect to y. And for the last components to be the same, the partial derivative of f with respect to z is equal to lambda times the partial derivative of g with respect to z, and then we still have that constraint equation where g has to be equal to the given constant k. So here we have a system of 4 equations and 4 unknowns, x, y, z, and lambda, and we're interested in finding the points x, y, and z that satisfy those constraints. So let's look at some examples making use of this method of Lagrange multipliers. In our first example, we'll consider a simple case where we're just working with the function of 2 variables, just to illustrate how the method works for a simple function. So here we are told to use this method of Lagrange multipliers to find the maximum and minimum values of the function 6x plus 8y, where we're only considering points that lie on the circle x squared plus y squared equals 1. So for these problems, usually I like to start by giving my constraint function a name or some notation. So let's let g of xy be our constraint function. And here our constraint was x squared plus y squared has to equal to 1. Now we know for the method of Lagrange multipliers, we need to find the gradient of f and the gradient of this function g. So let's start by looking at the gradient of f. Here, the first component for grad f is going to be 6, and our second component would be 8. And the gradient of g would have a first component of 2x and a second component 2y. And we know by the method of Lagrange multipliers, if our function f has an extreme value at a point xy, these two gradient vectors have to be equal to each other, or scalar multiples of each other, at that point. So here we're going to set the gradient of f equal to lambda times the gradient of g. And so we find, equating the first components of those vectors, that 6 has to equal 2 lambda times x, and equating the second components of our vectors, 8 has to equal 2 lambda times y. And we still have to satisfy the constraint x squared plus y squared is equal to 1. We're only considering points that lie on that circle. So let's see what we have here. We're looking at the following system of 3 equations. And we can see from our first two equations that lambda cannot be equal to 0. If lambda were equal to 0, then our right-hand side of our first two equations would be 0, which could not satisfy those first two equations. So here, let's start by saying clearly lambda must be non-zero by looking at the first two equations. So if lambda is non-zero, I know I could divide my first two equations through by lambda, or equivalently 2 lambda. So this system of equations that we were considering above is equivalent to the following system. If I divide my first equation by 2 lambda, I have 3 divided by lambda is equal to x. If I divide my second equation by 2 lambda, I have 4 over lambda is equal to y. And we know that the sum of x squared and y squared has to equal to 1. So my first two equations give me expressions for x and y in terms of this Lagrange multiplier lambda. So I can take these expressions for x and y and substitute them into my constraint equation. So here, let's say substituting x and y into the third equation, we find x squared plus y squared would be equal to, our x value was 3 over lambda, so we have 3 over lambda quantity squared, plus y, which was 4 over lambda quantity squared, has to equal 1. So we're left with 9 over lambda squared plus 16 over lambda squared is equal to 1, or 25 over lambda squared is 1. So it follows that 25 is equal to lambda squared, and so lambda could be plus or minus 5. Now, once we have the values of lambda, we know that x and y are defined in terms of lambda. So we can substitute these values back into our earlier equations to determine the points of interest. So here, our points of interest are the points xy is equal to plus or minus 3 over 5 and plus or minus 4 over 5. And we're interested in determining the maximum and minimum values of our function. So here, let's evaluate our function at the points of interest that we just found and see what our largest and smallest values are. So here, our function f of xy is 6x plus 8y. So to get the largest value possible, I want to take x and y to be the largest numbers possible, which would be where we have a positive 3/5 and positive 4/5 for x and y. So in this case, we find the value of our function is 10, and if we evaluate our function at the smallest values for x and y, namely negative 3/5 and negative 4/5, the value of our function is negative 10. So these would be the maximum and minimum values for the function f if we're only considering points which lie on that unit circle. So here we get our largest and smallest values along with the points on the circle where those largest and smallest values occur. So let's look at another example illustrating the method of Lagrange multipliers in the case that we have a function of 3 variables. So in our second example, we are asked to use Lagrange multipliers to find the maximum and minimum values of f, which is x, y, z, for points that lie on the ellipsoid x squared plus 2y squared plus 3z squared is equal to 6. So we see in this example, if we tried to use the method that we were using in the previous section where we solve our constraint equation for z, it's not so easy to solve this constraint equation for z since it's quadratic in terms of z. We end up with a pretty messy function for f in that case. So if we instead use this method of Lagrange multipliers, let's start by giving our constraint function a name. Let's call it g of x, y, and z, which is the equation of this ellipsoid, x squared plus 2y squared plus 3z squared is equal to 6. Now to use the method of Lagrange multipliers, we need to find the gradient of f and the gradient of this constraint function g. So here, the gradient of f would have a first component of y times z, a second component of x times z, and a third component of x times y. And our constraint, or our gradient of this constraint function g, is the vector 2x, 4y, 6z. So using the method of Lagrange multipliers, we need to let the gradient of f equal to a constant lambda times the gradient of g. Which leaves us with a system of equations. In order for the first components of these vectors to be equal, we would have y times z is equal to 2 lambda x. Our second components would be x times z is equal to 4 lambda times y. And equating the third components, we have x times y is equal to 6 times lambda times z. And our constraint equation was the equation of this ellipsoid. We know that x squared plus 2y squared plus 3z squared has to equal 6. So we're considering the following system of equations, and this one's a little bit trickier to solve. Now, one way that we could go about solving this would be to look at the expressions that we have on the left-hand side of these first 3 equations. We have yz, xz, and xy. And if I were to multiply each of these equations through by a single variable, I can get the same expression on the left-hand side for all 3 of these equations. And the expression that I'm going to get, or that I want to get, is x times y times z. So the system we have here is equivalent to the system that I would get by multiplying my first equation on both sides by x. So we could have x times y times z is equal to 2 lambda x squared. If I multiply my second equation by y, we would have x times y times z is equal to 4 lambda times y squared. And if we multiply our third equation by z, we have x, y, z is equal to 6 lambda times z squared. And our constraint equation is still x squared plus 2y squared plus 3z squared equals 6. So now if we look at our first three equations, we see that we have the same expression on the left-hand side for all three equations, x times y times z. So we know that the quantities that we have on the right-hand side of these three equations must be equal to each other. So it follows that 2 lambda times x squared, that is the right-hand side of our first equation, must equal 4 lambda times y squared, the right-hand side of our second equation, and that's also equal to 6 lambda times z squared, looking at the right-hand side of that third equation. So if we were to divide through by lambda, we have 2x squared is equal to 4y squared, which is equal to 6z squared. So we could also divide through by 2, and we're left with x squared is equal to 2y squared, which equals 3z squared. And now taking these expressions and substituting into our third equation, or excuse me, our fourth equation, we can reduce our equation to a single variable. So let's see what we have. If we substitute into the fourth equation, we have x squared plus 2 times y squared, but now we know 2 times y squared had to equal x squared, so we have another x squared, plus 3 times z squared, which was also equal to x squared, is equal to 6. So we have altogether 3x squared equals 6. So x squared is 2, and x is then plus or minus the square root of 2. So if we solve for y and z, well, looking back at our earlier work, we saw x squared was equal to 2y squared. Now, if x is plus or minus the square root of 2, x squared is 2, and it follows that y squared would have to be 1. So y could be plus or minus 1. And if we look at our equation for z, we know that 3z squared has to equal x squared, which was equal to 2 if x is plus or minus the square root of 2. So z squared would be 2/3, and z is then plus or minus the square root of 2/3. So our points of interest in this example are the points x, y, z equal to plus or minus the square root of 2, plus or minus 1, and plus or minus the square root of 2/3. Now we want to evaluate our function f at each of these points that we found. But we can save ourselves a little bit of work if we think about the function f that we're trying to maximize or minimize. Our function f is the product of x times y times z. Now we see for any of these points of interest, x, y, and z have the same magnitude, but might be positives or negatives of one another. So in order to get the largest value of our function f, we could take the positive product of x, y, and z, and to get the smallest value for the product of x, y, and z, we could take the negative of the product of these x, y, and z coordinates. So here we find the maximum value of our function f is the value of f when we have two, we say all three of our values as positive or two negatives and a positive, and the value of our function at that point would be a positive square root of 2 times 1 times square root of 2 over square root of 3, which leaves us with 2 over the square root of 3. And the minimum value of our function f would be the negative of the product of square root of 2, 1, and square root of 2 over square root of 3, which would be negative 2 over the square root of 3. So here we have the largest and smallest values of our function, along with the points where these may occur. So we see from this second example that in the case we're working with a function of 3 variables, it might be a little more difficult to solve the system of equations that we get by equating our gradient vectors for these functions f and g. So let's look at another case of this method of Lagrange multipliers. In the first two examples that we've been considering, we are trying to optimize a function of 3 variables subject to a single constraint. And in some examples, we might be trying to find the extreme values of a function f subject to 2 constraints. So maybe something of the form g of x, y, and z is equal to k, and we have a second constraint, another function h of x, y, and z has to equal to a different constant. So we have a Lagrange theorem, or a method of Lagrange multipliers, in the event that we have 2 constraints. And here's what our theorem says. If our function f has an extreme value at some point x naught, y naught, z naught, then there exists numbers, lambda and mu, such that the gradient of our function f at the point x naught, y naught, z naught is equal to lambda times the gradient of our first constraint function g plus mu times the gradient of our second constraint function h evaluated at the point x naught, y naught, z naught. So when we're looking for where a function has its extreme values subject to 2 constraints, we're going to set up this equation for our gradient vectors and find all the points x naught, y naught, z naught that would satisfy this equation given in Lagrange's theorem, and then evaluate our function f at all of those points of interest to see what our largest and smallest values are. So let's look at an example of this. In this last example, we are asked to use Lagrange multipliers to find the maximum and minimum values of the function xy plus yz, which would lie on the curve of intersection of the cylinders xy equals 1 and y squared plus z squared equals 1. So here we have our points that we're considering must lie on the curve of intersection of 2 different surfaces. So we have 2 different constraint equations. We're only considering points which lie on both of these surfaces in order to lie on their curve of intersection. So as with our earlier examples, let's start by giving these constraint functions a name. In our first constraint, we have a function g in terms of three variables, really here just defined in terms of x and y, is equal to x times y, which has to equal 1. And our second constraint function, h, of x, y, and z, is given by y squared plus z squared, which has to equal 1. So in order to set up our equation for the method of Lagrange multipliers, we need to find the gradient vectors of f, g, and h. So let's start with the gradient of f. So here our first component would be y. Our second component is x plus z. And our third component would be y. The gradient of g would have a first component of y, second component of x, and it didn't depend on z, so our third component would be 0. And the gradient of h would have a first component of 0, second component 2y, and a third component 2z. So using Lagrange's theorem, in the case that we have two constraints, we want to let the gradient of f equal to lambda times the gradient of g plus mu times the gradient of h. So let's see what this gives us. Looking at our first components, we would have y is equal to lambda times y plus 0. Equating the second components, we would have x plus z is equal to lambda times x plus 2 lambda times y. For our third components, we would have y is equal to lambda times 0 plus mu times 2z, which gives us 2 mu times z. And then we have our two constraints. We have to have x times y be equal to 1, and y squared plus z squared equal to 1. So here we have a system of 5 equations in terms of 5 unknowns. And for reference, let me number these equations. So here we will number these 1, 2, 3, 4, and 5 so that I can refer back to these later in my work. Now using our first equation, we see that y has to equal either 0 or lambda is equal to 1. Now we know, looking at our first constraint equation, that y cannot be equal to 0. Otherwise, it does not lie on the curve xy equals to 1. So here, we can say by equation 1, we know lambda has to equal 1. The reason being, otherwise, y would have to equal 0, which doesn't satisfy. Our fourth equation. So using our first equation, we have lambda must be equal to 1. Now, if we were to substitute lambda equal 1 and equation 3, which says y is equal to 2 mu times z, into equation 2, let's see what we get. So the left-hand side of equation 2 is x plus z, which has to equal lambda times x plus 2 lambda times y. Now if lambda is 1, we have x plus 2 times mu. Let's see, this should be mu here in my second equation. So lambda times x plus 2 mu times y, not lambda times y here. So we would have then 2 mu times y, and equation 3 says that y is equal to 2 mu times z. So we're left with, if we subtract an x from both sides, z is equal to 4 mu squared times z. Now we can divide through by z, and we have 1 is equal to 4 mu squared. So mu squared is 1/4, and mu is then plus or minus 1/2. Now, if we were to substitute mu equal to plus or minus 1/2 into our third equation, let's see what we have. So equation 3 says that y is equal to 2 times mu, which is plus or minus 1/2 times z. So y is equal to plus or minus z. Now, looking at our fifth equation, let's see what equation 5 tells us. Here, our fifth equation becomes y squared plus z squared. Now, if y is equal to plus or minus z, then z squared would be equal to y squared, which is equal to 1. So we have 2y squared equals 1. Y is then therefore plus or minus the square root of 1/2, or 1 over root 2. And z was equal to plus or minus y, so z is then also plus or minus 1 over the square root of 2. So we still need to find our x values, and if we look back at equation 4, for our first constraint, we saw x times y had to be equal to 1. So by equation 4, we have x times y is equal to 1. So if y is equal to plus or minus 1 over the square root of 2, x has to be plus or minus the square root of 2. So altogether, we find the points of interest are the points where x is equal to plus or minus the square root of 2, y is equal to plus or minus 1 over the square root of 2, and z is plus or minus 1 over the square root of 2. Now, the function that we're trying to maximize or minimize is x times y plus y times z. So evaluating that function at each of these points that we've just found, we find the maximum value of our function f is given by 3/2, and the minimum value